So I am, as it was said, I'm going to talk about our data processing unit, our BlueField unit, and I'm going to talk about it in the context of east-west traffic. That is, a context of running large jobs, not so much going out to storage in this particular case. There are a lot of uses for the DPU, but what I'm going to talk about today is really focusing on work in the east-west direction within the system, within a single job. So when you think about traditional server architectures, typically you have the host with all its computational capabilities and the like sit, whether they're CPUs, GPUs, or whatever, they sit separate from the network. The network's sort of off to the side, and the host side does quite a bit of work to progress communication, whatever it happens to be, storage or other. And so with this new DPU, well, it's not so new; it's third generation now. There's a new architecture that we're going towards, in which you have the DPU as a much more capable entity sitting adjacent to the host. So it can do a variety of things, whether it's storage, whether it's security, progress communication libraries, or the like. And so this is the model that we're slowly building up towards supporting within our systems. And so I'm going to talk today specifically about how we use the DPU for communication library acceleration. So for those of you that are not familiar with the DPU, I have a quick cartoon here at a very high level describing what the DPU is. So as I said before, we're on our third generation of the DPU called BlueField 3. At a very high level, the DPU is a system on a chip. It includes a network core, or in the case of InfiniBand, it's both InfiniBand and Ethernet. It's the ConnectX core. It also has ARM CPUs. Depends on which generation you're at as to how many CPUs are actually there. These CPUs run Linux. They run your standard compilers and the like. They run your standard code, so it's very easy to generate code that will run on the DPU. It also has memory controllers and the like. So that's it. At the hardware level, that's what it looks like. At the software level, we have a suite of software called DOCA, Data Center on a Chip is what it stands for. It has a variety of libraries that are used to ease the use of this device. Now, I'm talking about these details in terms of how you use it and the like. The goal here is for a lot of users not to even have to know about these details, but for those that want to go and optimize things, for those that have very special use cases where there aren't general purpose type of solutions available, these are the sort of tools these are libraries that ease the use of the system. So they include things like security, network libraries, communication libraries, and a variety of other things. So from a performance perspective, on the left of the picture here, I have a comparison of the capabilities of BlueField 2 and BlueField 3. So if anyone in the room has used BlueField, they most likely use BlueField 2. And BlueField 2 to BlueField 3 is a big change in terms of what you can do with it and how useful it can be for production workloads. And so at BlueField 3, your nominal network bandwidth increased by a factor of 2. So we went from the HDR generation of InfiniBand, for example, to the NDR generation of technology. Message rates go up. Again, that's a factor of the core, the network core that's sitting in there. The number of compute cores is doubled. It depends. You don't have to use all of them, but you can run up to 16 cores on the DPU. And of course, the number of cores that you run determines how much power you take. So you can run 8 cores and fit within the PCI limit, 75 watts with no issue at all, actually even a lot less than that. But some of the larger core counts that use all the memory and run the chip as fast as they can go up to around 150 watts or so. So you need an extra source of power to operate the device. Computational capabilities have increased significantly by a factor of 5. Memory bandwidth has increased again by about a factor of 5, which is very significant. Because that means with BlueField 3, you can actually saturate the network with data that's BlueField resident. There's some another capability exists with BlueField, in that you can use the BlueField card to generate network activity, whether it's sending data, receiving data, or the like, on behalf of data that's host resident. And that's important because what that means is if you want to move data from between hosts, the DPU is capable of generating that activity without copying the data from the host to the DPU, which of course would kill your performance. It would have your network bandwidth double your latency and the like. So this is a very useful feature when you're trying to stage data, whether it's storage data, I/O data, or the like, from the host to some sort of wherever, to some other destination, without actually having to increase the cost of PCI traffic, latencies, and the like. So I thought it would be worthwhile just talking very briefly about some design considerations in terms of how to use this device. And the fact that, for example, that it has compute cores doesn't necessarily mean that you want to go and do all the computing you could possibly do on that device, and other things like that. So probably from my perspective, one of the most attractive things, attractive features of the DPU is it's an asynchronous device. So we've always wanted to be able to overlap computation, communication, but with standard designs, you always have the compute and the portion of the network drivers competing for the same compute resource, right? So you can't do both of them simultaneously. You have to time slice between them. With the DPU, this is now really possible, and this is probably the most beneficial, from my perspective, one of the most beneficial features of the DPU. It does have compute limitations. So these are not server-grade processors. They're not intended to be server-grade cores. These are cores that are intended to let you do some extra things away from the main host, to offload a lot of service work from the main host to the data processing unit, to the DPU. And so it's very important whenever you design these sort of, think of how you're going to use this device in the context of your workload, not to give it too much work. So if you give it too much work, it will become the slow portion in your overall job run, and actually potentially slow your job down. So that's an important thing to take into account. Yeah, those are probably some of the main items there. There are some accelerator engines on them. There's some compression, decompression engines, depending on which generation of the device you have, and a few other things aimed specifically at storage. A few details on implementation. So we've done a lot of work in terms of offloading MPI or SHMEM or the like to the DPU. So using the DPU as a progress engine for communication within the application. So in a host-only model, I have here in blue, UCC is the communication library that we use. It stands for Unified Collective Communication Library. It runs within the context of a process in your normal MPI implementations, for example. What we've done in the DPU offload is we've extended the definition of the MPI process to include both the CPU and the DPU, right? So the DPU will do work on behalf of the host, and of course it requires coordination. Just a high-level view of sort of a highlight in terms of how we use this library, how we take advantage of these benefits. I have a portion here of a collective communication operation that sort of shows what we do to offload the implementation of a collective communication onto from the host to the DPU. So when a host makes a call to a collective operation, say your MPI all to all, MPI all to all v, something like that, it basically tells the DPU that it started, that the collective has started, passes it down a bunch of metadata, and at that stage the DPU takes over running the collective. So the communication, so that the host now is free to do other things. Those other things may be still continuing to process the same collective if you're doing a collective, if you're using a blocking collective, or in the case of computation, it can continue doing the computation as this collective is progressed by the DPU. The arrows there going from rank 1 DPU to rank 0 DPU and back to rank 1 basically show you how you would transfer data. So the DPU is initiating data. The DPU that belongs to rank 1 is initiating a read from the data that's resident on rank 0, and it sends it to rank 1 without any involvement of either CPU. And at the end of the operation, after all your collective is done, there's acknowledgement back to the MPI process that it's done. So this all happens in the background. This is what you would do if your data is really large. For small data, you would do something else. So I won't talk about a lot about software perspective. So as I mentioned before, there's this implementation is done in the context of UCC, which is an open source communication library. For those of you that are familiar with UCX, for example, that's used quite a bit. This is in the same family of software. Just supports the collective communication. There are a few changes, a few pieces that are added to the library to make this work side by side with other collectives. From a model perspective, the CPU typically, if you're using this with a CPU, you typically have a lot more computational cores than you do cores on the DPU. And so what we do on the DPU is we run these processes that are called service processes, and each service process will be a server or will work on behalf of several MPI ranks or MPI processes on the host. Typically a ratio of 10 to 1 is the way I think about this. So this is another thing to be careful, because if each process gives it too much work, again the DPU is going to be overwhelmed and not be able to perform well. Let me skip that. So I'll close here with a slide describing a bit, or several slides talking about the actual performance of this implementation. So the first collective we decided to optimize was the all-to-all V collective for large data. We did this because there are a fair number of weather codes, for example, that use that collective. And I have here we've measured here the latency of an operation in the context of running at 1,000 processors at different message sizes. So this is an optimization for larger message sizes. We've compared here the performance of OpenMPI 4, which is current version of OpenMPI, HPCX, which is the MPI that NVIDIA ships. That's based on OpenMPI with some of our own optimizations, and then the performance that we get when we use the DPU to offload those collectives. And so what we see here is sort of what we would expect, is that the raw performance HPCX and the DPU offload are similar. And that's really what we would expect, because we're not doing anything, we're not moving any less data, we're using very similar algorithms. So on their own, this is the performance that we would expect. I should say what we're in the process of doing is moving the DPU, support for the DPU into our HPCX product, so it will also be available there. When it comes to all-to-all V, we've measured the performance as a function of the number of service processes that we use on the DPU. And bottom line here is it only takes about four service processes, a ratio in this case of 1 to 8. We've gotten most of the performance advantages that we can out of using the DPU we've sort of close to maximize the performance of the DPU. Again, this is 1,024 processes as a function of message size. In terms of overlap, so supporting overlapping computation and communication, the DPU version is close to 100% all the time, but that's not surprising, right? Because that's what it's designed to do. It's designed to be an asynchronous engine, and all this is showing is it reached its, it does what it's expected to do. Whereas host-based models, because they're sharing compute and network activity, the overlap isn't nearly as good. However, when you go and look at applications, the picture is very different. We've measured. We have data here for 4 applications. We've actually run this, done performance measurements on more than just these 4 applications. But these happen to be applications that were mostly important in the context of procurements. So P3D-FFT is a 3-dimensional Fourier transform library. We compare the performance of that library using the offloaded version versus the host-only version, and we see about 17% improvement in the Fourier transform. This is using a non-blocking collective. So what we're seeing here is the benefit of overlapping, of being able to progress asynchronously, overlapping computation and communication. This is the top right shows the performance for a weather model running again on 1,024 processes, and we see that we get about 7% improvement in application performance. And here we use a blocking all-to-all V. So even in the context of blocking, we're able to get improvement in performance. Now this isn't so much. This is not unexpected because we've changed the algorithms that we use here, and basically we're able to detect processes that are late to the game and not block the application progress with that. We did the same thing for physics. It's actually a DFT code out of the Max Planck Institute. The name of the code is Octopus. We get 17% improvement here when we use a blocking all-gather V. And again, another weather code from Japan. We get about 6% improvement in performance. So what we see that this certainly has some ingredients to speed up at least CPU-based codes. The same algorithms that we've developed here are also useful on CPUs if you have spare CPUs and GPUs. So that's the next thing one of the next things we'll look at. I have a much more complete set of results. If anyone's interested, we have a paper on Wednesday in the conference that goes into a lot more detail on the algorithms and what we do. So if anyone's interested, you can join. Thank you.